Okay. Hello, everyone. My name is Xiang from Primus Labs. So yeah, this talk is about a little bit about like cryptography behind zkTLS, but yeah, I'm not going too deep in that part because it's too complicated, and I'm going to show something like maybe new in this space about how you like extending zkTLS to other like tools or like applications. Yeah, I think like Thomas already like introduced the background of zkTLS. So essentially like enables the problem is that we want to like the client to prove that they actually have some data from like Web2 servers without changing or modifying anything about the server side. So this is the most challenging part, because if you can modify the server side, just sign everything and it's done. So yeah, so that's why we focus on TLS, so like 1.2 or 1.3. So the one of the main like standard use case is that can I prove to another person that I have enough like ETH in Coinbase? So this is kind of like a very standard use case. Yeah, a little bit. Don't be afraid about this kind of cryptography side. A little bit about TLS, because we're going to show why it's important. Like we choose this kind of technology there. So essentially, like TLS has two parts. The first part is handshake, meaning that the client and the server have to negotiate with a session key. So it's kind of like key exchange, and after they get the same like key material, they have to expand this kind of keys into a very long key, like session key. And the second part is the record phase, means that the client, the server who has a symmetric shared key, that can communicate, encrypt and decrypt with this symmetric key to send the message and receive messages. So essentially that we are considering this kind of like KDF, key expansion, or AES, GCM, these two parts. So why I'm saying this thing is that, yeah, just one single, like, they look like this way. All I want to say that they are very complicated. And another thing is that if you are familiar with ZK, so these kind of functions are Boolean circuits. So which means that all existing like ZK stack is not like it's not like suitable for this kind of circuits. So that's why in a lot of cases, we don't want to choose like existing ZK stacks. So we have to develop a new text to make it much more efficient. Sorry. So yeah, there's like actually 3 modes, but I don't want to talk about TE right now. So I only talk about like MPC or proxy. So that's very simple differences between these 2 modes. So like MPC means that the client, a verifier, or like the tester, they act as a TLS client by running this kind of 2 PC protocol, like MPC protocol. And the proxy model is that the verifier sits between the client and the server. So all the traffic goes from the verifier to the server. So these are the 2 main differences. But we have different like trust assumptions, and we have different performance in these 2 modes. So essentially, just very simple like explanations of this. So when you're using MPC, so why is it so expensive? Because you have to run like 2 pieces between the verifier and the client to compute these kind of key expansion circuits, AES circuits, and at the end of this computation, you also have to run zero-knowledge proof systems to prove that the KDF and the AES runs correctly. So it's kind of combination of like MPC and the ZK steps. So it should be like very expensive and very like inefficient. So like the very original like Deco paper, yeah, I think that's a very nice paper. So they kind of use a very complicated like authenticated Garbled circuit or ZK stacks. So it's quite slow. So you can have like memory problems, like communication problems. So one of our contributions is that, okay, we improve that by like more than 10 times faster. Like we're using much more simple Garbled circuit and QuickSilver. So everybody is using QuickSilver right now, but QuickSilver is a zero-knowledge proof system, but it's not like ZK stacks. I'm going to introduce a little bit later, but the thing is that for MPC TLS, these are the 2 like the most expensive part. So we are like trying to improve that part. And so in the MPC part, so what's the bottleneck of MPC? So we're kind of now using Garbled circuit. I'm not going to introduce what is Garbled circuit. It's kind of like a two-piece protocol. So they have few features. First of all, they're cost around, which is a benefit because you don't need to care more about the latency. And the second part is that for every single boolean circuit, like AND gate or XOR gate, you have for one AND gate, you have to send like 256 bits to the verifier, which is very large. And in our paper, I think it's the most efficient one that for 1 KB request, you have to send like more than 23 megabyte. So this is actually the main bottleneck here. So essentially, like in your real applications, the bandwidth is very small. So you have to send a lot of data there. And for the proxy, there is a lot of ways you can use a proxy mode, and it's very simple. So first, the verifier get all the ciphertext between the transcripts, and then the prover, the client, just prove in zk that I know everything about that. So this the framework is very simple, but the details we have a few applications. We have a few choice there. Like in our Garbled proof, we prove that the KDF and AES from the very beginning. So this is okay because QuickSilver is very efficient in proving Boolean circuits. So it takes less than 1 second to do that. And different versions, maybe I think Reclaim, they are now using to prove AES using zkSNAC, using GNAC. So it's kind of maybe you have a few memory problems when you're proving large content. And also they want to use a recursive proofs to prove that. So it always has performance issues in the prover side when we want to generate with zkSNACs. So that's the problem. And why QuickSilver is so good for zkTLS? Because QuickSilver is interactive in our proof system. So interactive means that the prover have to interact with the verifier, and it's not publicly verifiable. It's not. But it's very suitable for this case because in zkTLS, it's not necessary to be non-interactive. It can be interactive. And as I said before, for KDF and AES, using zkSNAC is very, very efficient. But they're all Boolean circuits, so we can use the QuickSilver to prove it very, very efficient. And there's no memory issues. There is no proof size issues. And even you can run everything inside Chrome extensions, mobiles, very single social limited environments. So that's why we choose interactive ZKP, or that's why we choose QuickSilver. So here's kind of numbers. So when you're proving AND gates, you can use less than $2 to prove 1 trillion gates. So it's very, very cheap. It's super cheap. And you also can prove our arithmetic circuits, but in zkTLS, you don't need to do that. So, and we have different versions to run in different platforms, and that's the main reason we now want to use QuickSilver. And they actually have a better version right now, maybe. So let's forget about all the details. Let's talk about the comparison of these two modes. So first of all, let's take a look at the efficiency. So of course, proxy TLS is much faster because there's no MPC things, which is the main bottleneck of zkTLS. It's much, much faster, more than 10 times faster. And for the trust assumption, there's different. First of all, you have to trust the server. Otherwise, there's no way you can solve this problem. And yeah, there's always an assumption that there's no collusion between the client and the verifier. So that's the main problem I think all of the projects want to solve. And we have some solutions I'm going to introduce later. And for the proxy TLS, there's another assumption. It means that the verifier has to ensure that he's connecting to a server. Otherwise, there is a kind of man-in-the-middle attack. So a malicious a malicious client can then sit between here. So it's like the client talks to himself, and he has a private session key. Then he can like sign everything. So this is the major, like I think, assumption and the debate on how to choose MPC or proxy model of these two ways. So if you are not proving that very sensitive data, and you care about performance, maybe you can choose TLS, proxy TLS, because it's kind of harder that for the client to sit between, to process this kind of man-in-the-middle attack. And there is few performance numbers. So actually, we have a paper about that, and we do the experiment that for like in 18 areas that we show that all these kind of MPC TLS can work well with QuickSilver. There's no like timeout issues. And also we push the limit of using proxy TLS that we can prove very large content, like 200 kilobytes image that is actually generated from ChatGPT in under like 2 minutes. Maybe I think it's much faster right now using like Bronze extensions. So that's why I think in using like QuickSilver, you can prove very, very large like content. And I don't think we can do that with zkSNARKs because you always have like memory issues there. Also, we do have new ways to improve the whole efficiency, like Garbled circuits. So the main bottleneck of Garbled circuit is that you have to send a lot of like messages to the verifier. So we have a new paper of what we call bitGC, meaning that you only need to send 5 bits, which is like 50 times smaller communications. But it's not practical right now because the computation time is very slow. So we only have like 55 AND gates. And now using the original Garbled circuit, we can do like 10 million AND gates. So it's kind of very impractical right now. And we also have a non-interactive version of QuickSilver. We call it MPC in the nerve. It's kind of a version of MPC in the head. So you can see it as a non-interactive version of QuickSilver with the same performance. So this means you can make the proxy TLS non-interactive. And then you can reduce a lot, like 4 to 5 rounds in the MPC TLS. So it's kind of ongoing like work. We're gonna like deploy it maybe in the next year. Also, yeah, I want to actually there is kind of requirements from our customers, and there is kind of I want to show that there is restrictions of these two modes, especially for IP restrictions. So in a lot of applications, when you like connect to the server, there is kind of like IP restrictions for that server side. So in the proxy model, the IP is always from the proxy. So be careful. In some cases, the data source will block it if it's not from the real users. And for MPC, if that depends on the form of your product. If you are running a cron extension, so the IP is still from a proxy. The reason is that, like standard cron or Safari, there's some set the raw TLS API there. So you have to use like a proxy to initiate the TLS session. So there's kind of be careful about that. But you are running like a customized browser, or you run it in the backend. So it's okay because the IP is actually from the client. So this is actually some restrictions we got from our customers. So when you like deploy your products with zkTLS, to be careful of this kind of IP restrictions, which is very important. And yeah, here goes to I think the most interesting part is the collusion of clients of the attester or malicious attesters. Because all the existing like zkTLS solutions actually doing this way. So the client prove to the verifier or the notary or the attester that he has some kind of data. After that, the verifier will issue an attestation, which essentially like a signature or that. So, which means that the verifier or the tester has a secret key. They can sign the attestation. So, if the verifier is kind of malicious, so they can sign everything. So if you're using zkTLS to secure fund, so be careful that who is the attester, because otherwise they can just sign everything and get the money back. So in all these cases, now a tester is too powerful. And especially when you're using them to secure fund, then it's very dangerous. So we need decentralized testers. So that's the main problem we want to solve. And we try a few solutions. First of all, I think it's similar to like to maybe Reclaim their solutions. So yeah, we can have multiple testers. So if the client want to do this zkTLS proof, they actually do one zkTLS proof with each attesters. And as long as the majority of the testers sign, okay, it's okay, then you get the like the valid attestation. But there's a few questions there. First of all, so you have to run multiple times of zkTLS, which means that the performance is like the number of testers times slower. You have to run like independently. And the second part is that this is not suitable for like frequently changing data, because you have to spend some time to run the zkTLS protocol. So during this time, the data may change. So you don't know which one is the correct one. So this is not very like practical in real use cases. So we explore that, but it's not like quite suitable for our cases. And the other part is that it's kind of theoretically it's kind of perfect way. Means that we also have multiple testers there, and when the client talks to the testers, they actually run the MPC. Means that there is like file party. They run a file party computation protocol to just like it's an extension to the 2PC protocol. And this is theoretically doable. We actually have algorithms try to explore the performance there. But the issue is still like the performance, very, very bad performance. For like, it's like 10 times the number of testers times slower in terms of computation and the communication. So in high probability, it's gonna be like timeout of the TLS session. Theoretically it's doable, but in practice, is very, very hard for our fast to deploy. So when you try these two things, so okay, how to solve that? Maybe the thing is that we use TE. So we actually built this network and it's already alive. So first of all, we put all the testers in TE, which so means that there is, you cannot do bad things inside TE. Second thing that we are not running like MPC or something like that. We are using blockchain. We now deploy on base. So there is kind of smart contract. So every single user wants to use this kind of TLS service, zkTLS service. They go to the blockchain, and the smart contract, we randomly select one of the testers, and then you run the zkTLS service there. So in this case, it's not just simply put your attester codes inside TE. There is kind of more like requirements of doing that. So first of all, even the manager of the testers cannot get the signing key. So they cannot see anything about the signing key, because otherwise they can sign anything they want. And the second thing is that they have the ability to deploy multiple instances without changing the signing key. This is the most difficult part of using TE, because the original TE actually generates the secret key in the hardware. So when you deploy multi-instance, the key will change. So this is in order to enable one attester can deploy multiple instances without changing the signing key or the address. You have the support inside the TE here. And also, you need to a very strict version control to make sure that, okay, even a third party who is deploying this attester software, they have to be strictly follow the open source code in case that they can change anything and they can do bad things. So the challenge here is that we need properties of TE to we need TEs to support these kind of properties. We can make this network to be secure. And now, yeah, we have a solution that we use for DStack. So DStack supports all of these features and is open source, and you can deploy in different TE providers. It's not just Intel or something or other providers there. So we're using combinations of DStack and our proxy model, MC model to build this kind of zkTLS network. So this makes sure that, okay, we can bring in third-party attesters. Yes, that's what we are now doing. So we are calling for attesters. So the goal is that we want to build a more decentralized network. And the good thing is that if you can be one of the tester, we can share the revenue of the network. We now, 80% of the network fee goes to the testers, and the 20% of the fee goes to the network. So this means that you have the chance to get the revenue to cover your cost when you're running the TE side. So we now have a few testers like Succinct, TKP, or Fala. So we are now talking to more testers that it can ask the testers in the network to secure the network. So that's our solution for make it more decentralized. Yeah. So yeah, I'm going to say something new right here. So I think people did not mention about this is that in real applications, zkTLS is not enough. It's not enough at all. So why? So let's take a look at attestation here. So essentially, you have a lot of URLs, means that what kind of data or the source of the data, the link there, and you can use zkTLS to prove that you have different data here, and also you have address and signature. This is kind of very standard attestation when you're doing this selective disclosure. So the thing is that in attestation, the data is public, and there's no very efficient way or very developer-friendly way that you can do further computations on that. I think Thomas also mentioned that you can do actually in the paper we had do you can do hash, or you can do different commitment on that. But when you are thinking about this very complicated business logic, QuickSilver right now is not enough because we do not have a VM. And when it goes to the real applications, you have to handle circuits using QuickSilver, which is not developer friendly. So can we? The question is that can we combine zkTLS with other tools, like zkVM, like FFH, like MPC, that we can extend this zkTLS part, the data verification part, to a computation part? So that's the thing we're now doing. So we came up with this new thing about what we call data verification and computation mode, especially that not only that you can authenticate the source of the data, and everything is private in the attestation, and you can also do more computations and for any kind of customized functions. So this is the thing we want to combine together. This is actually needed in the real applications, not just authenticated some kind of public data in a data source. So this is what we now promote to our customers, and is already deployed by our customers. And also we have a few things about this, like combined with MPC and combined with FHE stuff. I think Dimitri is gonna introduce more details about this. We have a paper about this, but the thing I want to choose, I want to say is about how to combine with like zkVM or any kind of zkDSL you can use. So in our network, you can actually using zkTLS to generate this kind of attestation, and all the data is actually hashed or committed by using hash-based commitment here. And you can also apply different zkVM or zkDSL to customize your own logic, business logic. So in this program, you have to prove 3 things. First of all, the signature there is valid. Second, the hash of the plaintext is valid. And also you have to prove that this kind of data actually satisfy the customized function or customer logic. You can define that. You can use zkVM and use zkDSL to customize the logic. So this is kind of a new framework we came out that when we talk to our customers, they actually want this part. Because the logic is always hard, it's always very complicated. It's not just comparison, it's not like just like very simple like addition. It's very complicated functions here. So that's why we're gonna like use these kind of things for more like new applications there. And we now support with Succinct. They have a private proof network using KVM. And also we have supported like Brevis, a new like zkVM. I think Michael gonna talk more about this this afternoon. And we also have like Aztec Nova to be integrated. And this is collaborating with like Hashclock. So it's already open source right now. So you can actually, in general, you can combine any kind of new like zkTLS or zkVM to zkTLS together to this DVC like mode. And yeah, this is also like one of challenge in our tutorial if you want to try. So we have like very detailed steps to help you to understand and to build these kind of new things. So at the end, I'm gonna like showcase some use cases using this DVC mode. So a very standard use case is that we actually provide this privacy-preserving proof of reserve for stablecoin projects to prove that they have enough assets off-chain, like in the centralized exchanges. So why zkTLS is not enough? So the first of all, it's privacy-preserving, means that the stablecoin projects do not need to leak in their positions and the strategies in the centralized exchange accounts. And first of all, they can get their asset distributions. I think it's multiple URLs. It's not just one single data. It's multiple data because they have multiple accounts using zkTLS. And we also use zkVM to filter, aggregate the amount of different assets. You don't know what kind of assets they have, so you have to write a Rust code to filter, to aggregate everything. So it's not possible right now for using just using QuickSilver. It's very suitable to use zkVM Rust to do that. And also we have info file with personal trading data in centralized exchanges. Means that in a lot of, in this application, they want to want the users to prove that their average trading amount in the last 30 days is larger than some threshold. So first of all, you have to use zkTLS to retrieve all the trading data. It's a very long list. But it's okay using QuickSilver to all the kind of history, trading history there. But you also use burst zkVM to analyze. Okay, I have enough. The average of everything is okay, and generate some kind of proof there. So it's always combinations of the source verification and the logic of your business. And we put this kind of business logic into zkVM or any kind of zkDSL. So this is kind of real applications, real solutions deployed in our customers to show that the power of DVC. So yeah, essentially the goal for us is that we want to build a decentralized zkTLS network. And essentially we want to combine these new tags, zkVM MPC or FHE, so to unlock the future of private data-driven applications in Web3. So I think this is actually the future of leveraging zkTLS and other techs to build a new, especially financial-related or data-related or private data-related applications in Web3. Yeah, that's essentially the presentation.
Have you thought at all about the issue of the client needing to trust the attester with their data that they're sharing with them? So say, for example, it's a sensitive piece of information. How are you able to address that?
Sorry? Can you be more specific?
So let's say I'm visiting a site, for example, that contains sensitive information. Let's say I'm a journalist or something. And the plain text data that I'm sending to get a proof generated from, the client is having to trust the attester with that plain text data because it's effectively acting as a ZK middle box. How are you looking to approach that sort of problem of reducing the trust between the client and the attester?
Essentially, you don't need to send, the client don't need to send the plain text data to the attester. So when you generate the hash of data, you're actually using QuickSilver to generate about that. So you just send the hash of the data and you prove that the hash is correct. So in all these kind of scenarios, the attesters does not know anything about the data. They just verify there. So that's why it's secure.
I have a question. You mentioned that there is this need for decentralized attesters. Could you go into depth a little bit more? What does that mean or look like specifically? Is this multiple, creating redundancy in terms of the data being attested multiple times by different parties, and then you need to build some sort of consensus around that? Or, yeah, if you can.
Yeah, so for that, there's no consensus. So we actually bring different parties. We kind of different projects can be one of the testers. We whitelist their address. And when the users goes to use this ticket service, they kind of initiate a transaction in base to a smart contract. And that smart contract, we are randomly select, okay, you're gonna talk to which attester. So after that, the client and the selected attesters can run the zkTLS protocol off chain, and they can work in this way. So there's no consensus. Every single time the client only talk to one single attester there. So, but this attester is randomly selected, and everything's running inside TE. So even the manager of this attester cannot do anything about that. So that's the main, because we have to balance security and performance. So we do not, for now, we do not need the consensus. Yeah.
And then the goal here is to avoid the collusion between the.
Yes.
Got it.
Yeah. Correct.
Thank you.
Thanks. Do you think this scheme can be made to work with client certificates like MTLS?
Sorry?
Do you think this scheme could be implemented using client certificates with like MTLS, you know? Client-side certificates for TLS connections?
No. So the problem is that you don't, because in the traditional TLS, the client and server always has the session key. So if there is no way that to commit the ciphertext before the client get a ciphertext, there is always some ways that the client can change because they have the session key. So that's the portability of, it's not portable for TLS. So essentially that's why we need MPC or ZK to avoid that. So pure client-side certificate cannot solve this problem. It's very hard.
Maybe using MPC to set up the key previously.
Then you don't need the certificate for the client side, right? You just use MPCs is sufficient. Yeah, we tried that, but it seems that it's not quite suitable to solve the problem using MTLS. Yeah.
Don't you see in the future some way to do it, maybe?
I think it's very, very hard. So our direction is that we still like using like MPC stuffs. We still like to improve the MPC protocol, just not using like different TLS protocol. But maybe TLS 1.3 may be a good choice. Maybe, I don't know.
Thank you.
No.
If I understand correctly, the authentication of the server still depends on the TLS certificates, which basically means at some point there's TLS root certificates. Do you publicly commit to which roots you trust there? Are they stored in a smart contract?
For now, you just trust the certificate. Sorry. So yeah, in all of these zkTLS protocols, the verifier has to verify that the certificate from the server is valid.
Yeah, and this happens via checking this tree up until some certificate authority.
Yes.
But there are many different ones, and you probably, like, which set of those do you trust? Do you publicly commit to which ones you trust?
We actually bring all these kind of roots and check all the chains of the certificates. Yeah. We bring all the roots there. So essentially that you have a root there and you have a chain of certificates. So we check every single like the chains there in the verified side. So essentially like you trust the CA, right?
Yeah, but there are many CAs, right? I mean, I could just be a CA and set up my own tree of certificates, and at some point you're on my root, and then you trust me. Like
yeah, before you deploy things, you have to make sure that the root is actually the correct root of the website that you are accessing. So you have to check that before you deploy everything. Yeah.
Okay, and this you kind of have public, like which are the CAs that you trust? Is this like, do you publicly commit to this somewhere?
What do you mean by public commit to this?
I mean, like, it could be like Let's Encrypt, for example, right? It's one CA. And you could decide whether you trust them as a root CA or you don't. Like Firefox, for example, has them stored in the browser directly, in the binary or the roots that they trust.
Yeah, so first of all, you have to trust the TLS server, right? So then you have to trust the certificate of that server, right? And then you can enable the verifier to check the certificate of that server during zkTLS. So this makes sure that, okay, you are talking to the correct server. So that's the main method you can do.
Okay, yeah, thank you. Perfect.
Is it possible to use zkTLS for AI user data privacy and private inference in AI?
Depends on the applications you want to build. So essentially, it's very easy for you guys to prove that this data is actually generated by AI. You can prove that using zkTLS very, very efficiently, but you cannot do that like zkML stuff. Like zkML means that there is kind of proof to make sure that this data is generated or influenced by some kind of mode. You cannot do that. Use zkTLS. So that's a different thing.
And can you hide the user data?
You use zkTLS, you only can do that. The data is generated by this, like ChatGPT server. This is the only thing you can prove. Yeah, it's like because you access ChatGPT using HTTPS, so that's.
And original user input data, you cannot.
Oh, you can because when you access to ChatGPT, you actually type your content in the web and send to the server. So you also can prove this part. It's exactly the same about like using zkTLS. You can prove that this data is the input to your mode, and this data is the output of that mode. Depends on this input. You can prove this part.
But the data is open to the ChatGPT.
Yeah, data is open to ChatGPT, yes.
Sorry, I'm new to this ZK stuff, but I would like to ask, like, is quantum computing a threat to ZK, or we shouldn't bother about it?
That's a good question. Yeah, first of all, Garbled circuit and the QuickSilver is quantum resistant, so there's no quantum computer can break that. But like ECDSA, like ZK stuffs, you have such risk, theoretical risk. So yeah, maybe in the future you have like quantum secure like ZK proof systems, maybe lattice, you know.
Thank you.
Thank you so much. Time